Welcome. Today I'm presenting a complete layered integration architecture that connects Hermes AI agent with ROS2 Humble and NVIDIA Isaac Sim and Isaac Lab. This covers cross-machine deployment, synterial migration, and embodied intelligence. Here's our agenda. We'll cover the core layered architecture, two implementation approaches, cross-machine integration between Ubuntu 22.04 and 24.04, embedded edge device selection, critical pitfalls, seamless synterial migration, the industry outlook on ROS2, and a deep dive into embodied intelligence. Our architecture has three completely isolated layers. ROS2 Humble serves as the sole intermediate bus. Hermes and Isaac never connect directly. All communication flows through ROS2 for maximum stability. The upper layer is Hermes, the AI agent acting as the global brain. The middle layer is ROS2 Humble, the real-time message bus. The bottom layer is Isaac Sim and Isaac Lab, handling physics and simulation. Layer 1 is Hermes, the cognitive brain. It receives natural language commands like patrol the warehouse, avoid obstacles, collect footage. It decomposes these into navigation, vision, and grasping subtasks. Hermes reads simulated camera, LiDAR, and odometry for global decision-making. Critically, it never touches the Isaac API directly. It only uses standardized ROS2 tools. One codebase works for both simulation and real hardware. Layer 2 is ROS2 Humble, the real-time nervous system. It acts as a unified data relay hub. Hermes sends velocity commands and joint trajectories downward. Isaac publishes camera images, laser scans, coordinate transforms, and odometry upward. ROS2 hosts Nav2 and Move-it2 planners for real-time closed-loop control. This layer provides critical isolation, separating LLM inference latency from simulation physics cycles. Layer 3 is Isaac Sim and Isaac Lab, the physical body. It provides high-fidelity NVIDIA PhysX GPU physics rendering. It supports multi-robot parallel simulation environments and reinforcement learning training at scale. The built-in Isaac Sim ROS2 bridge extension provides automatic bidirectional ROS2 topic synchronization. This requires zero Hermes source code modification. Now for implementation. Approach 1 is the open-source ROS Hermes plugin, the fastest path. It is community-built and auto-discovers all ROS2 topics as Hermes tools. Setup takes 3 steps. Clone the repository, symlink the plugin directory, and launch. The result, Hermes automatically discovers robot move, get camera frame, scan obstacle, and navigate to goal. You get direct natural language control of simulated robots. Approach 2 is a custom MCP bridge for maximum flexibility. First, build a ROS2 Python node with read services for sensors and pose, plus write services for velocity and joint control. Second, wrap ROS2 services as MCP server endpoints using Fast API. Third, Hermes MCP client connects and registers tools in the skill library. This approach is best for custom simulation interaction, reinforcement learning feedback loops, and multi-robot cluster scenarios. Launch sequence is critical. If you get the order wrong, communication fails. You need 3 independent terminals sharing a unified ROS domain ID. Terminal A launches first, loading ROS2 Humble and the bridge nodes. Terminal B launches second, starting Isaac Sim with the ROS2 bridge extension. Terminal C launches third, starting Hermes agent. Always follow this exact order. For cross-machine deployment, we have 2 machines. Machine A is the workstation running Ubuntu 22.04 with ROS2 Humble. It hosts Isaac Sim, Isaac Lab, and Hermes agent. It handles simulation rendering, the AI brain, and reinforcement learning training. Machine B is an edge device running Ubuntu 24.04 with ROS2 Jazzy. It runs pure ROS2 with no Isaac components. It handles real robot drivers, Nav2 navigation, and Move-it2 motion planning. Humble and Jazzy cross-version compatibility is solid. Standard messages like geometry messages, sensor messages, and navigation messages are binary compatible. Fast DDS multicast enables direct cross-machine transmission without conversion. The only constraint is that custom message and service definitions must be compiled identically on both machines. On Machine B, you must explicitly set the RMW implementation to FastDDSCPP. For Machine B hardware, we recommend Jetson Orin NX or Nano. It has native Ubuntu 24.04 and ROS2 Jazzy support, NVIDIA GPU with hardware-accelerated SLAM, YOLO, and camera decoding, plus GPIO and can bus for industrial motor drivers. Raspberry Pi 5 is only suitable for simple robots. It lacks a dedicated GPU, so HD multi-camera streams will stutter. It can only handle basic differential drive control. We maintain a strict communication boundary between machines. Machine A handles high-level decisions at a slow loop of roughly 1 to 10 Hz. This includes natural language parsing, global task planning, sending goal poses, and receiving compressed sensor snapshots. Machine B handles low-level control at a fast loop of 10 to 1000 Hz. The local closed loop means the robot survives network loss safely. Here are the critical pitfalls you must avoid. First, Python version conflicts. Always source ROS2 with Python 3.10 before launching Isaac with Python 3.11. Second, ROS domain ID mismatch. All components must share identical domain IDs. Third, never direct connect Hermes to the Isaac API. This causes process blocking, GPU contention, and vendor lock-in. Fourth, firewall issues can block multicast communication. Sim-to-real migration requires zero code changes. In simulation mode, Isaac outputs through the ROS2 bridge, Hermes reads camera and scan data, and sends velocity commands back through the bridge to move the virtual robot. In real hardware mode, physical sensors output through ROS2 drivers, Hermes reads the same standard topics, and sends velocity commands through nav2 to motor drivers. The Hermes agent code is 100% identical. Regarding Gazebo, keep it but you will not need it. It is not needed because the physics engines are incompatible, ODE versus PhysX GPU, the scene formats are incompatible, SDF versus USD and URDF, and reinforcement learning with high-fidelity vision requires Isaac only. It is safe to keep because there are zero background processes when idle, the topics are naturally isolated, and it only uses about 100 megabytes of disk. There are 3 architecture modes depending on your stage. Pure simulation uses only Machine A. Everything is virtual, for algorithm validation and RL training. Debug mode uses Machine A plus a laptop as Machine B, 2 computers for cross-machine DDS testing. Production mode uses Machine A plus a Jetson or Pi 5 as Machine B. Machine A handles simulation and the LLM brain. Machine B runs real motors and sensors. This is the final deployable mobile robot architecture. The industry outlook is clear. ROS2 is here to stay. NVIDIA's entire product strategy is built on ROS2. Isaac ROS provides GPU-accelerated perception, all ROS2 based. The Isaac Sim ROS2 bridge is the official communication standard. All robot demos from Turtlebot to humanoids use ROS2. Direct Hermes to Isaac connection fails because of vendor lock-in, resource contention, and the lack of real-time control and standardized debugging tools. Embodied intelligence requires all 3 layers working as one system. Hermes corresponds to the prefrontal cortex, handling language, planning, and memory. ROS2 corresponds to the cerebellum and nerves, handling sensor fusion and real-time control. Isaac and Jetson correspond to the body and senses, handling physical interaction and action. The complete loop, Hermes thinks, ROS2 plans, the body acts, sensors feed back, and Hermes confirms. Let me correct a common misconception. VLM and VLA are just one component, not the whole picture. Many people think VLA equals embodied intelligence. In reality, VLM and VLA are analogous to the visual cortex only. They cannot handle real-time control, multi-sensor fusion, motor dynamics, or distributed hardware coordination. Complete embodied intelligence equals VLM and VLA as the cognitive piece, plus ROS2 as the control hub, plus the physical body. Let's compare ChatGPT with your embodied system. ChatGPT has no body, your system has Isaac simulation or a real robot. ChatGPT has no senses, your system has cameras, LiDAR, and IMU. ChatGPT has no physical feedback, your system creates action, environment change, and new perception in a continuous loop. ChatGPT outputs text. Your system has ROS 2 millisecond level closed loop control. ChatGPT is brain only. Your system is brain plus body plus loop. Here are the 6 key takeaways. 1. 3 completely decoupled layers. Hermes is the brain, ROS 2 is the nervous system, Isaac and Jetson are the body. 2. ROS 2 is the irreplaceable middleware. There is no bypass for production systems. 3. Sim-to-real migration requires 0 Hermes code changes. 4. Machine B should be a Jetson or Pi 5 embedded device. 5. Embodied intelligence spans all 3 layers. 6. This layered architecture is the industry standard for the next 3 to 5 years. Thank you for your attention. I am happy to take your questions and discuss the Hermes agent, ROS 2, and Isaac Sim integration architecture. This concludes our presentation.